Hey, how you guys doing today? This is Colin, also known as CYIT on YouTube, and today we'll be explaining the Bitneater 8-bit computer random access memory module. So, I think a good question to ask ourselves is what exactly is random access memory? Well, random access memory is the main memory of our computer and it's used to store data that is actively being processed by our CPU. Keep in mind, random access memory is volatile, meaning that if we ever lost power to our computer, we would also lose the data stored in our main memory. Here's what a single bit of data looks like in our two 74LS 189 64-bit memory chips. These single bits of storage are multiplied by 16 rows and 4 columns, which come together to make 16 rows and 8 columns, or 16 words and 8 bits of data, meaning that we can store 8 bits of data to 16 separate locations or addresses in our memory. This is the reason why random access preludes memory, because we can read or write data to or from any of the 16 different locations in our memory. But how exactly do these memory addresses work? With 4 binary digits, you can represent a total of 16 different numbers ranging from 0 to 15. All zeros in binary is the decimal number 0. 0001 in binary is the decimal number 1. 0010 is the decimal number 2, and so on. This is how we can determine which separate memory locations we'll be reading from or writing to. Here's our dedicated memory address register. In run mode, we'll use the 74LS173 4-bit register to load a memory address from the bus. Addresses are stored only on the rising edge of each clock signal and only when our load signal is low. The outputs of our 74LS173 4-bit register are connected to our 74LS157 quad 2-line to 1-line multiplexer. In program mode, we will use a dip switch to manually input a memory address. When our dip switch is in the off position, no current can pass through, and because our multiplexer defaults to high, that individual memory bit will be 1. When our dip switch is on, current from our multiplexer can pass through the ground, causing these individual memory bits to be low or 0. Our quad 2-line to 1-line multiplexer is a device that can take 4 sets of 2 inputs and direct one set of 4 bits or the other to the output. In this case, the dip switch is connected to the multiplexer A inputs and the 4-bit register to the multiplexer B inputs. Our multiplexer will be connected to the address inputs of our two 64-bit memory chips, which are wired together, but before this, we can see the output on these 4 LEDs. This switch allows us to select whether we will operate in run mode or program mode. Because ground is connected to the center pin, when the switch is in the right position, it will allow current to flow from this 220 ohm resistor to ground through our green LED, indicating run mode, and the same will occur for our red LED indicating program mode. Our red LED is connected to the select pin of our multiplexer. When strobe is low and select is low, we will output the A input, and when strobe is low and select is high, we will output the B input. In this case, strobe will always be connected to ground. Okay. Our selecting mechanism, which is also connected to our address register multiplexer select pin, also routes to these 3 74LS 157 multiplexers in our data input section. In run mode, we receive our data inputs directly from the bus. And in program mode, we receive our data inputs from this dip switch just as on the memory address register. The two multiplexer outputs, which come together to form an octal 2-line to 1-line selector, are wired to the 8 bits of data inputs for our two 74LS 189 memory chips. To write this data to our memory module, we use the active low write enable pin tied together on the two separate chips. In run mode, we will use this control signal to write data. Here's the NAND gate with the clock signal and control signal as inputs. The output of this NAND gate will result in a 0 only if our two inputs are 1, and this will cause the active low write enable to read our data from the multiplexers. The resistor capacitor circuit is used to create an edge detector that will only read data on the rising edge of the clock signal, which will result in improved synchronization. On the left clock signal, the capacitor will charge almost instantly and then begin to resist the flow of current. Once the clock turns off, the capacitor will discharge through the resistor. The clock signal input will only be on for as long as it takes the capacitor to charge. In program mode, we will use this push button to connect both of its terminals together, resulting in pulling our write enable pin low and loading from the data on our dip switch to our memory modules. Because the 274LS189 outputs are inverted, we will reinvert them with these inverters and send them to our 74LS245 output buffer, but not before the signals are connected to these LEDs so we can see what's stored in memory. By bringing the 74LS245 enable signal low, we can output to our bus.